Okay, we've already seen this phenomenon of overfitting to noisy data on the programming slash MATLAB side. So let's actually quickly review what we just saw. Okay, so this little lecture is about overfitting and ways of avoiding overfitting by using the optimal model complexity. And we will also touch upon things called training and testing, cross-validation, and so on. Okay. So the sort of question that we motivated through polynomial regression is what degree polynomial should we use to fit the data? Or more generally, if we have a sequence of models of increasing complexity, um, what model complexity should we use? Should we use the simplest possible model, or should we use the most complex model that completely fits the data? Okay. And like I said, this is perhaps one of the most central questions in all of machine learning and learning theory and so on. Okay, and just to recap, if you have an mth degree polynomial, it's got m plus 1 coefficients. And if you have n data points, then we can find a polynomial that of degree at least n minus 1 that exactly passes through all the data points, right? Specifically, we can make the mean squared error exactly equal to 0. And our question was, is this good? And we already saw evidence that it's not necessarily a good idea. And it's not a good idea because data usually has error or noise. And it may be that the true model is actually not a polynomial, right? It's actually not a polynomial. So if we fit a high order polynomial through the data, what we would be doing is basically fitting a polynomial through all the noise, which sounds like, at least superficially, a bad idea. This phenomenon is called overfitting, right? So you have noisy data and you try to fit a model that tracks all the data that you have as well as possible, including potentially all the noise, and that's called overfitting. Okay, so here's just a visual illustration. We have some data points, and this red line is meant to be a very simple model that doesn't necessarily pass through all the data points. It just sort of roughly captures the trend of the data. And then the green line is meant to be a more complex model that passes through all the data. And the green line we might call overfit model, sort of passes through all the data. And the problem with overfit models is that they typically generalize very poorly on new data, right? Because they've been essentially sort of bent into shape to fit the noisy data that you do have. If you get some new data, or if you use data that you have not seen before, this weird curve might not actually fit that new data point very well. So here's a picture of that. So you draw some, you have this overfit curve, and you might have a new data point. That new data point might actually be roughly following along this linear trend, maybe somewhere out here, but it might be pretty badly predicted by this overfit curve, or at least much worse predicted than this linear trend. Okay, so the idea of overfitting is related to a number of things that we see in our daily experience. I would say overfitting is like memorizing all the data you've seen. It's like as good as memorizing all the data you've seen. And if you want to make a sort of analogy related to studying for an exam, overfitting is like studying for an exam, studying for only the questions that will be on the exam, kind of, right? Not exactly, but it's kind of like that. And if you ask a question that's not necessarily among the questions that you've studied for, that sort of thing might not generalize very well. Okay, so what should the polynomial degree be? Okay, like I said, more generally, what should the model complexity be? Okay, And then method one is when you actually know what the typical noise in the data is, right? Um, and what you do is you fit different models of different complexity, and you compute the mean square error, and you actually compute the root mean square error. This needs to be corrected. It's RMSE. You compute the root mean square error and then equate it to the standard deviation of the noise in the data, which is assumed to be known. Maybe you're using a sensor, and the sensor has a particular noise level, and you've characterized that using independent measurements. And if you know that standard deviation, you should find that model, or in this case, that polynomial model that has the root mean square error that is closest to the noise level in the data. Okay. Um, and this assumes that the noise level in the data is zero mean. Okay, so that's method number one, and this works only if you know the noise level. Method number two works even if you don't know the noise level, and I'll talk about that in the next short video.